Hi everyone. This week we will recap the data structure and algorithm concept. As you have already learned this course before, and this is very important for application development role. In this lecture, we are going to talk about something crucial in computer science and programming: algorithm efficiency and complexity analysis. The question is, what is algorithm efficiency? So, what exactly do you mean by efficiency? When we talk about an algorithm being efficient, we are primarily concerned with two things. First, time efficiency. It represents how fast does the algorithm run. We measure this in terms of the number of operations an algorithm performs, not necessarily the actual clock time, as that can vary based on the computer speeds. Second is space efficiency. It represents how much memory does the algorithm need. This includes the space for the input data and any extra space the algorithm uses during its execution. The question is, why care? Well, an inefficient algorithm can be slow and consume a lot of resource, making your program sluggish or even unusable, especially with large datasets. Think about searching a database with millions of records or sorting a massive list. Because of that, efficiency matters. Next is measuring efficiency. How do we measure this efficiency in a standardized way? We use something called asymptotic analysis. This might sound fancy, but it's essentially a way to describe the algorithm behaviors as the input size gets very large. We are interested in the growth rate of the algorithm resource uses. We don't focus on exact operation count because those can be complex and hardware dependent. Instead, we look at the order of growth. We use some notations to represent efficiency or complexity like big O, big omega, and big theta. Now, big O notation. It represents the upper bound. Big O describes the worst case scenario or an upper bound on an algorithm's running time or space uses. It tells us that the algorithm won't take more than a certain amount of time or space as the input size and growth. For example, if an algorithm is big O n square, it means its running times grow at worst quadratically with the input size n. If you double the input, the time might roughly quadruple. Okay, in this graph, you can see the CGN. The CGN is represent the upper bound, and this fn function represent the actual runtime of the algorithm. So you can see after this n naught, for every input n, this CGN will always be greater than or equal to fn. So you can see the definition: a function fn is said to be big O gn if there exists positive constant c and n naught such that for all n is greater than equal to n naught. So you can see fn is always be less than equal to cgn. Then we can write complexity with big O notation like fn equal to big O gn. Next is big omega notation. Big O omega describes the best case scenario or a lower bound. It tells us the algorithm will take at least this much time or space. So if an algorithm is omega n, it means its running time will at best grow linearly with the input size. As you can see in this graph, here fn is the actual runtime of an algorithm and cgn represent the lower bound. And after every input, after this n naught, this fn will always be greater or equal to this cgn. So you can see the definition: a function fn is said to be omega gn if there exists positive constant c and n naught such that for all n is greater than equal to n naught. And this Fn will always be greater than equal to Cgn. Then we can write our complexity like Fn equal to omega Gi. Next is Big Theta notation. Big Theta provides a tightly bound. This means the algorithm's growth rate is bounded both from above and below by the same function. Essentially, it's saying the algorithm's performance is precisely characterized by this growth rate for large input. Suppose if an algorithm is theta n, it means its running times grows linearly, not just in the best or worst case, but consistently as n gets large. Here you can see in this graph, this function fn, actual runtime of the algorithm, will always be lies in between the upper bound C2gn and the lower bound C1gn. So you can see the definition. A function fn is said to be theta gn if there exists positive constant C1, C2, and n0 such that for all n is greater than equal to n0. So this fn will always be greater than equal to C1gn and always be less than equal to C2gn. If this condition is true, then we can write our complexity like fn equal to theta gn. Next is common complexity classes. Let's look some common complexity classes. First, constant time represent big O1. This is the dream. The algorithm takes the same amount of time regardless of the input size. For example, if you are accessing an element in an array by its index, it will take the same time whether if the array has 10 elements or 10 million elements. Another example is push or pop operation from a stack. That also takes the constant time order of 1. Next is logarithmic time, and it is written as big O log n. Algorithm with logarithmic time complexity becomes slightly slower as the input size increases, but they scale incredibly back. Each time you double the input size, the number of operations only increase by a constant amount. For example, binary search in a sorted array. You repeatedly divide the search interval in half. If you have 10 to the power 6 items, it takes around 20 comparison, not 10 to the power 6. Next is linear time. The linear time, it is represented big O m. Here the running times grow directly proportional to the input size. If you double the input, the running time roughly doubles. For example, searching for an item in an unsorted list or array. Finding the maximum element in an array. Simple loops that iterate through all elements work for comparisons. Next is linear arithmetic time. It represents by n log n. Here big O is missing. So this is big. This is very common complexity of or efficient sorting algorithms. It's slightly worse than linear but much better than quadratic. For example, efficient sorting algorithms like merge sort, heap sort, and quick sort. Quick sort in average and best case. Next is quadratic time. It represents big O n square. The running times grow proportionally to the square of the input size. These algorithms can become very slow with large input. For example, simple sorting algorithms like bubble sort, insertion sort, selection sort, or if you are writing a code which have nested loop, where both loops iterate n times. For instance, comparing every element in the list to every other elements. Next is cubic time. So it represents big O n to the power 3. So this also, here there are some algorithms like Flood Vassal algorithms in graph algorithms and like Bellman code algorithms, which require 3 nested loops. So because of that, it takes order of n cube. Next is exponential time big O to the power n. Algorithms with exponential time complexity are generally considered very slow and practical only for very small input size. The running time doubles with each additional input item. Finding all, for example, finding all subsets of a set. The recursive solution to the Fibonacci sequence, or the traveling salesman problem solved by brute force approach. Next is analyzing code. How do you figure out the complexity of your own code? So, for iterative algorithms, we will look first iterative algorithms and then recursive algorithms. So, in iterative algorithms, first is count operations. So, always identify the basic operation inside your loops and outside your loops. Okay, so how many operations are there? Then analyzes the loop. It's generally a single loop that runs n times is typically big O n. Nested loop often lead to polynomial complexity. For example, a loop inside a loop, both running n times gives big O n square. If a loop divides the problem size, half in each iteration, so that become a big O log n. Next is sequential statement. So edit the complexity of sequential block of code. And last is conditional statement. So for the conditional statement, always consider the worst case path in the conditional statement. Which block of the conditional statement is taking the maximum time? That consider that for the worst case. So like for this example. So this is the function to find max in a list, data list that contains the n elements. So here if you just look the each instruction, and you can consider that each instruction takes order of 110 constant time. Okay, so this is a constant time operation. This is a loop. Okay, so this loop is running how many elements we have in the data list, that number of times. So we are assuming that we have n elements. So this loop will run n times. And the elements and the instructions which are coming inside this loop will also run n times. And this max value equal to item, it is depends on the condition. So we are just assuming the worst situation. So this will also run n times. And this is last instruction, this will run constant time. So in this way, you can see what is the maximum amount of time an instruction is taking. So this is the loop block that is taking n time. So for complexity, we ignore the constant terms and we only pick the rest or magnitude of n as a complexity. So the overall complexity for this code become big O n. Second example you can see. Here this is the function print pairs that also takes data list. That size of data list is m. And here you can see two nested loops are running. So this first loop is running n time. And for each value of first loop, item 1, the inner loop will run n times. Okay. And the split statement will also be run n times. So for one element of the outer loop, this inner part will run n times. So total we have n iteration for the outer loop. So that means n into n times this inner part will run. Okay. So overall complexity will become order of n square for this total. And similarly, suppose if you have two blocks of the code, just we sequentially write the previous code and this code, then what will be the complexity of overall? So the previous, we generally select the max of the first block of the code. What is the complexity for that? That was big O of n, and then thus this block contains the complexity big O n square. So we take the overall complexity as a max of all blocks of the complexity. So the overall complexity will become n square if we have the two sequential blocks. So one is running after the another. So in this way, we calculate the complexity for the iterative code. Second is analyzing code recursive algorithm. So for recursive algorithms, there are two things we follow. First is recurrence relation. It defines a recurrence relation that describes the algorithm's running time. This expression Tn in terms of T for smaller input. So generally we write this recurrence relation. See, we can see this example. So we generally write the recurrence relation like Tn equal to Tn by 2 plus 1. So what does it mean? So Tn is the overall time for the binary search algorithm, and it actually calls recursively the same binary search function on the half of the input. Apart from that, it takes constant time to compare the middle element. So we always find out the middle element, we compare the middle element. After that, we figure out that which part of the input list our element may be exist. Based on that, we decide which part we need to search again. So that comparison takes constant time, and after that, we call the same binary search function on the remaining half of the array. So that is the time for the next recursive call. So in this way, this recurrence relation represents the overall time. After that, we calculate this time complexity with some methods. So like that methods we have we have recurrence tree, we have master theorem, we have iterative process. So here we can solve this. Suppose we are solving this just by the expanding way. So we can simply expand this equation like this. So Tn equal to Tn by 2 plus 1. Instead, so here you can see if an input is n, then our recursive call taking half of the input. Okay. So instead of this, we can write a new expression like 2 equal to Tn by 4 plus 1. So instead of Tn by 2, we will write here Tn by 4 plus 1 and the previous plus 1. Okay. So in this way, if we expand further, so we can replace this part like Tn by 8 plus 1 plus 1 plus 1. Okay. So how much time we can write this Tn by 8? So because you can see this divide value 2, then it is, and every time it is W. 2, then 4, then 8. So how many steps we require to reach at the end? So that in log n steps, so like you're writing like 2, then 4, then 8, then 16. So in this way, you will reach at n in log n steps. So each time we required a constant time, one time for the comparison. So in log n, we require this log n comparisons. So overall complexity will become order of log n for this operation. So this is the way how we can calculate the recurrence relation to complexity. We have the another example like merge sort. In merge sort algorithms, we have basically two parts. One is the merge part and another is the merge sort part. So merge sort part basically divide our input list into the half till our list contains single elements. And the merge part actually combine two sorted list into a once final sorted list. So in this way, so merge operation takes order of n time, and this recursive merge sort part. So the recurrence relation for this is Tn equal to 2Tn by 2 plus n. So this n is required This is required for merge function, combined to sorted list into a first sorted list. And these are two calls. So we have initially n elements. In the first step, we divide into a two half the list, then further we divide. So every call we have n elements. We calls our merge sort algorithms into the both half, left half or right half. So because of that, these two recursive calls are there, and each recursive calls are on n by 2 elements. So the time for each part is tn by 2. And apart from these two recursive calls, we have this order of n time for merge operation. So how we can solve this? So we can use different methods for this, like we have recurrence tree. So we can just make a structure how these calls are going on. So initially we have one called tn, and from this we have two recursive calls, t n by 2 and t n by 2. And each time it will take n time of merge. Next step, it will further divide, so t n by 4, t n by 4, and here plus n by 2 for merging, and same for this, t n by 4 and t n by 4, and plus n by 2. So overall time of on this level, n by 2 plus n by 2, it will become n by n actually. Okay. Same, next it will divide t n by 8. So you can see there are 8 calls, and each will take n by 4 for merging. So we can write like this, n by 8 into 8. So overall time at this level is also n. And you will reach at t1 in log n levels. Okay, so if we consider these levels, so in log n levels, you will reach at t1, and that is the base case for merge sort. So you can see each level you have n time, and we have log n level. So and overall complexity will become n into log n. Okay, so we can write like n log. So this is the complexity for merge sort. So in this way, we can calculate the complexity for recursive code. So you can explore this in more detail. So like recurrence relation, how we can solve the recurrence relation with the help of recursion tree, master theorem. You can explore this. And next is space complexity. It's about how much memory an algorithm uses. So first is input space, the space needed to store the input data itself. And second is auxiliary space, the extra space used by an algorithm like temporary variable, data structure, or the call stack in recursions. So these are the additional space which required. So like, for example, bubble sort, where the input space is required, we go n, that is required to store the input list. And we generally use some temporary variable to just set the variables or some basic purpose. And that is takes as a constant space. So we generally consider auxiliary space is required, we go 1. At the same time, merge sort, where input space is required, we go n, because we are getting list of n elements. But here we need a additional list to apply the merge process. So because of that, here auxiliary space, apart from the input space, we required before of n. Finally, what are the practical implication and trade-off? So first is data structure matters. The choice of the data structure heavily influences algorithm efficiency. For example, searching is faster in a hash table, that is big O of 1 on average. Or a balanced binary search tree is big O log n. And then in an unsorted array, that is big O of n. So we are performing the same operation, searching, but that is taking different times on different data structures. Because of that, data structures matters. Second is algorithm choice. For the same problem, different algorithms can have vastly different efficiencies. Always consider the expected input size, which is very large. And big O n square algorithms might be fine for n equal to 100 for small input, but terrible for when n is very large, like 10 to the power 6. Okay, so suppose we are sorting some elements that have 10 to the power 6 elements, and one algorithm is taking n squared time. So that will take too much time. But at the same time, if we have another algorithm that is taking n log n time, so that will take less time compared to the n squared time. Next is trade-off. Sometimes there is a trade-off between time and space efficiency. You might be able to make an algorithm faster by using more memory or vice versa. And next is premature optimization. Don't optimize too early. Write clear, correct code first. Then, if performance is an issue, profile your code to find bottlenecks and optimize those critical parts. Readability and maintainability are also important. So that's it for today. Thank you for watching.